The ocean energy buoy is a buoy which converts wave energy to electrical energy. The action of the waves force water to rise and fall in a chamber within the device, causing airflow to a turbine that produces rotational mechanical power. A prototype was launched and evaluated with success. Hence, the next phase was to fit the device with a turbine and electrical power takeoff to evaluate its electrical generating capacity and to gather operating data in a variety of sea states. When compared with other predictions, it will close the loop on the device's design process. The power takeoff system must provide a means of converting pneumatic energy to electrical energy and to dissipate this energy safely. Thus, it should provide means to several different requirements shown below. Also, note that the energy for the turbine must be from an onboard electrical power source, and the generated energy must be stored or dissipated on board. The turbine used is a Wells turbine type, able to produce unidirectional mechanical torque in the presence of bidirectional airflow. For a limited time test phase, the brushed DC machine was chosen as it has advantages over the other machine choices. However, for a production scale device, the use of a lead-acid battery bank for the turbine starting power was deemed the most reliable and cost-effective solution. It was also verified that an air-cooled resistive load bank would provide suitable means to dissipate the generated energy. It was recognized that the project represented a significant engineering challenge. A system must be developed quickly, which can be deployed quickly, the first prototype of which works as flawlessly as possible, and where avoidance of post-deployment issues is essential given the high cost of downtime and rectification. In order to meet these requirements, a design philosophy with the following qualities were developed: robustness, maintainability, usability, environment suitability, and safety. The operation of the power electronic system can be divided into two modes: motoring, which provides a controlled torque from the electric machine to accelerate the motor, shaft, and turbine from standstill to a defined operating speed; and generating, which applies a controlled torque to the turbine shaft via the electric machine, whose torque opposes the pneumatically generated turbine torque, maintaining a substantially constant shaft speed. Combining motoring and generating mode components, together with some mode switching and safety features, results in the final power electronic circuit below. A large number of sensors are used to provide control loop inputs and condition monitoring data. These include electric machine voltage, electric machine current, OWC chamber pneumatic pressure, turbine start battery voltage, and 24-volt service voltage, machine speed optical sensor, and temperatures of key components. After much testing and analyzing, the control system has a number of requirements to fulfill. Note that a decision was made at an early stage to utilize a programmable logic controller to implement these control functions. Testing of the system in the laboratory was facilitated by the construction of a test rig to test the power electronics operation and the tuning of the system control loops. After, the device was deployed and all preparation possible had been performed ashore, but even so, some electronic assembly had to be performed as part of the deployment. In operation, the PTO system proved a success. The hardware and software worked correctly from the day of deployment, with only two minor adjustments. During the testing period, data was collected for a range of sea states which was processed to create a power map for the device. There were no failure events in the power takeoff system, and sustained and successful operation was achieved. This graph shows the wave heights for the month of January 2009. A weekly electrical power output summary for week 3 of the same month is illustrated. This graph shows speed and power results in moderate sea, while this graph shows speed and power results in a heavy sea. Graph illustrating electrical power output variation with turbine rotational speed. Some recommendations and conclusions made were: a connection to the mains electrical grid onshore at a suitable voltage level should be considered for offshore wave energy test sites. Also, the design philosophy for the system is a valuable guideline for similar projects. Any system designed for this application should follow the design philosophy. And lastly, any project in the area should be cognizant of the testing issue in wave energy conversion devices and plan for a test power source to mimic input during commissioning.